So last time we were talking about circular motion, and we found the equations for circular motion that depended on position. If you need to move someplace, that's fine, but if you can see. So we had a circle. Let's go ahead and try a circle here. Hello. We had a circle. Here's our x and y axes, and we had an angle theta. And we said that the x position would be r, whatever r is, times the cosine of theta, and that the y component, or the y position, would be r sine theta. That's just basic geometry, right? Basic trigonometry, okay? And what about the velocity? So here's the velocity of the object. So here's the radius, my arm, and this right here is the radius. It goes, or sorry, is the velocity going counterclockwise. Right now, when it passes 0 degrees, the velocity is in the y direction, and it's not horizontal at all. And as it moves up like this, etc. Now, let's go ahead and go to a position right here. Notice this is the vertical. Notice that that angle is opening. Can you see it? This angle right here is opening as this angle is opening. Let's draw that a little bit more exaggerated. So if here is the angle with the x-axis, and here's the velocity, then this is theta. Well, if that's true, then the x component is in the negative direction, and it's sine theta, because it's opposite that angle. Well, this is going to be Vy, and that's going to equal the positive cosine of theta. Okay, I kind of was able to write that all right, vertically. So, that gives us these equations. I guess I don't need that here in a second. We just proved that. It tells us that v in the x direction equals negative v times the sine of theta. And v in the y direction equals v cosine theta. All right? And hopefully you remember that the derivative of cosine is negative sine. And the derivative of sine is cosine. So those seem to be fitting. And our acceleration always points to the center of the circle. And we found out that our acceleration in the x direction, take the derivative again, and you get negative a cosine theta. And the acceleration in the y direction equals negative a sine theta. Okay, those are beautiful. If you have the angle, you can figure, and you know, velocity, acceleration, etc., you can find them. But you know, it's actually two things. It'd be nice to be able to get away to just have that first equation and to be able to derive them. I'm a big fan of being able to derive things and not memorize everything. For instance, the kinematic equations. If you know that an object has a constant acceleration, so our acceleration function as a function of t equals a constant. That's actually right, constant, correctly. Well, since that equals dv dt, we know that we multiply by the t over here, and we get the velocity equal the antiderivative of the acceleration, which is a constant, times dt. Well, there's dt, the antiderivative of dt is just t. Plus your arbitrary constant was actually your initial position. Well, our velocity equals dx dt. So we find our x position, which would equal the antiderivative of this. Which gives us 1/2 at squared plus v naught t plus our initial position. By doing this, and just knowing that the acceleration is a constant, we can derive our kinematic equations. That'd sure be nice to be able to do this with the other ones. The problem is, there's actually two things going on here, but one problem is that velocity is the derivative with respect to time. And I don't see time there, do you? There's no time in those equations. And also in physics, don't we spend our time trying to define things? It would be nice to be able to say, at this angle, what's its velocity? At this angle, what's its position? But what about if the object is, when it's moving, you could say, but at this given time? at this given time. This is what we do in physics. We describe our world. Well, let's see if we can do this two ways. First of all, when we were doing the object going down a ramp, you said that potential energy equals linear kinetic energy or translational kinetic energy plus rotational kinetic energy, where this equaled, perhaps for well, one of the things people are really messing up is they think it's 2/5 all the time, but it's not. Like for a disk, 1/2 mr squared, whatever. And that the omega equals V over R. Does that mean that V equals omega times R? Aha, yes it does. Go ahead and put that in here. So we get that our velocity equals omega times R. That would mean that we put the negative in and we would have sine, but instead of theta, what goes in for theta? Well, theta has the units of radians. I'm not sure I put it up that, I didn't want it that high. So here's theta, which is in radians. And we want to have something that has seconds. And you remember radians per second, omega, which is in radians per second. And to get rid of seconds so that it equals radians, we have to multiply by seconds, which is time. And there we get an equation. That instead of sine of theta, we get sine of omega t. I'm going to move that down and put that in for the upper equation as well, and we're going to start to see something interesting. That would mean that our x position equals r times the cosine of omega t. Haven't you seen in calculus? Now again, I don't know where you are exactly in calculus, but I know our kids here have seen what's called the chain rule. And the chain rule says multiply by the derivative of the whole thing. The derivative of cosine is negative sine times the derivative of what's inside. And with respect to t, the derivative of omega t is just omega. Well, let's go ahead and do this and take the derivative one more time. Since acceleration is dv dt, well, that's going to give us sine, negative sine goes to negative cosine, omega t, multiplied by what's inside one more time. I wonder if that makes sense. Does that make physical sense? Does the units work out? Let's find out. Well, we know that a centripetal acceleration equals v squared over r. Well, since v equals omega times r, does it make sense that it's cosine though? Let's pick a spot. Well, yeah, so if we have our circle, and we have a position right here, okay, where that's theta, well, then isn't our acceleration towards the center of the circle? And if this is theta, then this would be our acceleration in the x direction, which would equal in the negative x direction times a cosine of theta, which fits. So we have just proven the chain rule in calculus. The chain rule, these rules in calculus have meaning in the physical world. So how is that useful to us? Well, now all we have to do is memorize 1 right there. So let's do that real quickly. We've done it a couple of times now, but let's do this. If x equals r times the cosine of omega t. We understand why it's cosine, right? Because you've got the angle here, it's adjacent in the x direction. If x equals r cosine omega t, then v equals dx dt, our basic definition of velocity, multiplied by the derivative of the whole thing. Cosine goes to negative sine, times the derivative of the inside, and our acceleration, which equals dv dt, Derivative of the whole thing, negative sine goes to negative cosine, multiplied by what's on the inside. You've memorized one equation, and you can derive the others. I want to point out two things here, and we're going to talk about omega here for a little bit. You see this cosine omega t here? Oh, sorry, let me make that even clearer. R times the cosine of omega t looks vaguely familiar. Therefore, A also equals negative omega squared times x. If you know x at some given position, and you know omega, square it, you can find your acceleration. Okay? Now, what is this omega thing? We need to get very specific now. Omega is defined as the angular frequency, has the units of radians per second, and is calculated in this way, where 2 pi is one circle. Hopefully you remember, right, that a whole circle is 2 pi, right? Divided by the period. I don't remember changing colors, but that must be just something that I needed to do. Just needed to change color, and I didn't even know it, okay? So let's talk about this period. In some years, actually in the future, with the AP 1 no longer teaching this in first year, I'm going to have to teach this from the ground up. So if you think about an object going around in a circle, start, 1, 2. It keeps doing the same thing over and over and over and over again. Or I have a book by Isaac Asimov that talks about this. And he says, imagine you could just take a stamp and you just go stamp, 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 stamp. The repeated part of the motion we call the cycle. The time, so this is called the cycle. And the time between here is the period. 1 period, 2 period, 3 period, etc. Right? So 2 pi over t. That would be circles per second. If we had an omega equal to 2 pi radians per second, well, stick in our equation there. Well, then t would equal 2 pi over 2 pi equals 1 second. It says my omega is 2 pi radians per second. That means it goes 2 pi, which is 1 circle, in a second. So I'm not sure I can't do this exactly right. So 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5. It just keeps going 1 circle every second. You cut it in half. So if you have t equals 1/2 second, then omega would equal 2 pi over 1/2, sorry, t would be over the period, which would be 1/2 second, right? Which would equal 4 pi radians per second. That means it can do a whole circle in 1/2 second, right? So it'd be 1 1,000, 2 1,000. It's going faster and faster. Okay? And since we call it the angular frequency, how frequent is this motion? The bigger the number, the more frequent the motion. All right? So, with these equations now, you can define an object in a circle. Given, so for instance, let's say that omega, let's use the one we just, well, if omega equals pi radians, pi radians per second, which means half a circle per second, right? Pi was only half a circle. So it'd be 1 1,000, 2 1,000, 3 1,000, 4 1,000. Not doing it perfectly, but half a circle every second, right? Well, if you wanted to say, let's try it out. So let's say x at 1 second. Well, that would equal the radius of whatever our radius is. We're just going to keep it r for right now. and the cosine of omega, which is pi times 1 second. The cosine of pi, when you're at all the way over here, hopefully you remember your unit circle, right? When the cosine is all the way at that side, it's a -1. Well, after 1 second, remember it takes 2 seconds to do a circle, so in 1 second it's over there. It's at the negative radius. Ta-da! It worked. And given that information, we could say, hey, we know how far it's going, we know how fast it's moving, in how many circles per second, as it were, and we know its radius. We could actually, let's give the radius a value. Let's say, 20 centimeters, right? So r equals 0.2 meters. Well, let's find our velocity. Well, the velocity equals dx dt equals the derivative, which is going to be negative omega r sine omega t. Let's put in what we know. The velocity would equal negative pi r, which is 0.2, times the sine of omega, which is pi times 1. Now, first of all, you see this right here? Way back over, let me see if I still have this stuff. There we go. Way over here, that's a long way off. Whatever is in front of there is the velocity. That is the velocity. So down here, if I can find it quickly, let me just shrink it and so I can find it fast. So down here, the actual velocity of the object, or the speed of the object, I guess I could say, equals 0.2 times pi, which is what? 3.14 times 0.2, so 0.6 something, right? So the actual velocity is, or speed is 0.6 blah meters per second. But what is the x velocity at 1 second? Well, you'd have to say the velocity at 1 second would equal this 0.6, whatever it is, times the sine of pi. What is the sine of pi? Anybody know? So the sine of 180 degrees is 0, which says at 1 second, its x component is 0. Does that make sense? Well, remember, it goes in 1 second, sorry, in a half a second, it goes an entire, let me see, what do we say? It's pi per second, right? Yeah, so in 1 second, it goes pi radians. So in 1 second, it goes from here to there. It ends up, so we'll just do it like, boom. It's over here. Well, here's this motion going straight up. Now it's got a y component. Whoa, there it is. I'll get to where the people can see it. It's going down. How much of down is in the x direction? None of it. It's correct. We know that the velocity at that moment is 0 meters per second in the x direction. But there would be a y component, which we could find. Likewise, we could use the acceleration, which equals negative omega squared r cosine of omega t, or equals negative omega squared times x. Let's do it both ways. At that point, remember that the acceleration points to the center of the circle. Well, if this is, so notice that I have my pencil, I'm trying to get to where you can see my pencil, pointing back at me. It's going this direction when the radius is over there. Well, in 1 second, it's going to be over here and it's pointing back this direction. So it should be a positive acceleration. Well, we get negative pi squared times the radius, which was 0.2, times the cosine of pi times 1 second. And the cosine of pi is the cosine of 180 degrees, which is -1, which equals, that will be whatever that is, I don't know. That's negative 3.14. We'll pretend that's close enough to 9 something, right? Times 0.2 times -1, flying away, which gives me, we're just going to say approximately equal 9 times 0.2 equals a positive approximately 1.8 meters per second squared. The rest of this just is a matter of practice. You have to do them over and over to understand these equations. Okay, that's it for today.